This video, we discuss learning outcome number 1 of lesson 6.1, which is all about comparing and contrasting discrete probability distributions and continuous probability distributions. Specifically, I'll want you to be able to describe the properties of continuous probability distributions. I'll also want you to be able to define the probability density function and explain its relationship to probability. Now, this learning outcome is alluded to in our text, but it's not explicitly covered. Now, before we get started, let's revisit the definitions of discrete random variables and continuous random variables. A discrete random variable has a collection of values that is finite or infinite but countable. So, for example, the number of coin tosses before getting heads is a discrete random variable, because you could have 1 coin toss or 2 coin tosses or 100 coin tosses or 1,000,000 coin tosses. Or if you have a weighted coin, maybe you never get heads, you get tails. But if you're counting that number of tosses, say you've got 1 toss, 2 toss, 3 tosses, and so on, even if it's infinite, even if you never get heads, it's infinite but countable. If we were to graph the values of a discrete random variable on a number line, it would just consist of a bunch of points like we've got here on this number line with 2, 4, 6, and 8. One example of a discrete random variable is the count of the number of movie patrons at a movie theater. So if somebody walks in the door and somebody presses a button on this counter, that counter is going to increase by 1. It's going to increment by 1 every time someone comes in. And that is a discrete random variable. It doesn't take on a range of values. You don't have all of the values between 277 and 278. You just have 277 and then 278. Now, with continuous random variables, that variable has infinitely many values that extend over a range. And this collection of values is not countable. For example, body temperatures. So there's a range of values associated with typical body temperatures, but there are actually infinitely many values on that range. There are infinitely many numbers in between that lowest body temperature and that highest body temperature. It's impossible to count all the items because at least some of them are on a continuous scale. So for example, if we're talking about the entire real line, we can't count all of the numbers between -infinity and infinity. Now, it wouldn't necessarily have to be an entire real line to be a continuous random variable. It doesn't have to, the values of the random variable do not have to go from -infinity to infinity. If you were just looking at all the values between 4 and 6, there are actually infinitely many numbers between 4 and 6. If we tried to count them, let's say I just drew a bunch of dots on here trying to count them, there would always be a little tiny gap in between my dots. So I would try to count those inside. But every time I try to count those inside, there's another gap and I would always miss some. That's what we mean when we talk about a range of values. Continuous random variables extend over a range of values, like the values on the real line or the values on some subinterval of the real line. Here's an example of a continuous random variable. If you're just measuring voltage in a smoke detector battery or voltage in any battery, voltage extends over a range. Now, before we get to chapter 6, I wanted to review what we talked about in chapter 5. Now, chapter 5 was based on material from chapters 2 and 3 and chapter 4. Basically, we're putting 2 ideas together. Now, you might remember back in chapters 2 and 3, we talked about summarizing and organizing data in tables, frequency distributions. We graphed that data with histograms. And then in chapter 3, we looked at measures of center. But that was all based on things that had actually happened in the past. So for example, if you were looking at 100 coin tosses, or actually 100 trials, of 2 coin tosses. So you'd toss the coin twice, and that would be 1 trial. And then toss the coin twice again, and that would be another trial. Toss the coin twice again, and that would be the 3rd trial, and so on. If we did that, and then we counted the number of heads in each trial, we might get an outcome, or we might have outcomes, that look like this, that look like what is summarized in this table. With each trial, you can either get 0 heads, 1 head, or 2 heads. And it looks like during those 100 trials, 27 of those trials had 0 heads. So they flipped the coin twice and they got tails both times. In 56 of those trials, they got 1 head. So one of them was heads and the other one was tails. And then in 17 of those trials, they got heads twice. So what we did back in chapters 2 and 3 was we said, okay, once we summarize this and organize this in a frequency distribution, and then maybe graph a frequency histogram to get some sense of the distribution, let's compute the sample mean and sample standard deviation as a measure of center and a measure of variation in that data. So that's past tense based on things that have already happened. In chapter 4, we learned about probability in general. If we were thinking about that trial of tossing a coin twice, we might think, okay, well, theoretically, what is the classical probability or the probability found using the classical approach of getting 0 heads or 1 head or 2 heads? In order to find those probabilities, what we would do is list that sample space, list all of the simple events that could occur if you're flipping that coin twice. So you could have heads and then heads, you could have heads and then tails, you could have tails and then heads, or you could have tails and then tails. And then we thought about what the probability of heads would be in 2 coin tosses for all the possible outcomes for the numbers of heads. So you could have 0 heads or 1 head or 2 heads. And we took the number of ways that you could get 1 head and then divide by the total number of outcomes. So there were 2 out of 4. And so that probability is 0.5. So chapter 5 said, okay, let's put what we did in chapters 2 and 3 together and create a theoretical model of expected results. Here, we'll list the number of heads as 0, 1, and 2, and we'll associate those with probabilities. That's 0.25, 0.50, and 0.25. So these are the probabilities, those classical probabilities calculated using that classical approach to probability that we discussed in chapter 4. But now we're listing it in a table like this, which looks a lot like our frequency distribution. So it's a combination of what we did in chapters 2 and 3 and 4. Now notice though that these probabilities are theoretical and they apply to the entire population. This is not just for a particular data set, but these are the probabilities for the entire population. In chapters 2 and 3, we were looking at sample data for 100 trials. Now, when we're over here in chapter 5, rather than looking at frequencies and using the frequencies to get a sense of the distribution, we described that distribution with these probabilities. And then we said, oh, since probabilities are based on expected results for the entire population, when we compute the mean and standard deviation here, we're not actually computing a sample mean and a sample standard deviation. We're computing the population mean and the population standard deviation. So those are population parameters, whereas over here in chapters 2 and 3, we calculated sample statistics. Okay, so that's what we did in chapter 5. But notice when we list the number of heads here, the number of heads was a discrete random variable. So this in chapter 5 was a discrete probability distribution. Chapter 6 deals with continuous random variables and continuous probability distributions. So we're going to do the same thing in chapter 6 that we did in chapter 5, but there are some changes that we have to make if X is a continuous random variable instead of a discrete random variable. So this slide is about contrasting those two. So chapter 5 deals with discrete random variables X, whereas chapter 6 deals with continuous random variables. In chapter 5, each X is associated with its probability. In chapter 6, we have something called a probability density function that describes the probability related to continuous random variable X. The graph of this probability density function is called a density curve. In chapter 5, the sum of the probabilities had to be 0 because one of those X values had to happen. Whenever we were looking at probability distributions, we were thinking about all of the possible values of that discrete random variable X. So if we add all of those up, we have to get 1 because one of those X values will occur. And then we represented that in the form of a probability distribution, which can be represented in the form of a table, or it can be represented in the form of a graph. Now in chapter 6, this probability density function looks something like this. And again, its graph is called a density curve. Rather than adding up all of the probabilities and getting 1 like we did in chapter 5, here probabilities are going to correspond to areas under the curve, and the total area under that curve has to be 1. It's just like summing up all of those probabilities over here, except now we're summing up something that is continuous, like this area under the curve. Now, if I wanted to visualize that probability distribution, in chapter 5, I might draw a probability histogram. Okay, so back to discrete probability distributions. These describe discrete random variables X. The values of the random variable can correspond to the possible outcomes. So if we're tossing a coin twice, we could have 0 heads or 1 head or 2 heads, and those are the possible outcomes. And then each X is associated with its probability. And the sum of the probabilities is 1 in order for this to be a true probability distribution. Now, if we want to visualize this, we visualize it with a probability histogram. Now here, the height of each bar is given by the probability of the given X. So the probability of getting 0 heads is 0.25. The probability of getting 1 head is 0.5. The probability of getting 2 heads when you flip that coin twice is 0.25. Now, if we add up these areas and we force the width of each of these bars to be 1, then the area of this bar is 1 times 0.25, so that's 0.25. And the area of this bar is 1 times 0.50, which is 0.50. And the area of this bar is 1 times 0.25. So we could think of areas as corresponding to probabilities here as well, provided that those bars are exactly 1 unit wide. But in general, maybe they're not exactly 1 unit wide. But if we add the heights together, if we add the probabilities themselves, we'll always get 1. Because if you're tossing a coin twice, for example, you will either get 0 heads, 1 head, or 2 heads. Those are the possibilities. One of those has to happen. You're not going to get 3 heads when you toss the coin twice. You're not going to get some fraction of a head when you toss the coin twice. You're never going to have a negative number of heads. These are it. So if we add all of those together, if we add those probabilities together, we should have 1, which means that one of those is going to happen. We're 100% sure, or we can be certain that one of those is going to happen. Now with continuous probability distributions, we've got something similar. Again, we've got this probability density function that's graphed here in yellow, and the total area under the curve equals 1, because areas are going to correspond to probabilities when we talk about continuous probability distributions. Now these describe the probability distribution of a continuous random variable X. So that random variable no longer takes on 3 values like 0, 1, or 2, or like when you're rolling a die, it no longer takes on 6 values, 1, 2, 3, 4, 5, and 6 as possible outcomes. With this continuous random variable, that variable takes on a range of values. That's why we need a curve to describe it. Now here, rather than associating each x with a probability, the distribution itself is described by this probability density function, sometimes abbreviated PDF. I will represent it by lowercase p of x. Now this doesn't give you the probability for a particular x value, it gives you the probability per change in x. Now this is really more related to calculus, and I don't want you to worry about it too much in our class. It's not that important, but I just wanted to be clear with you that p of x no longer means the probability that x is equal to that value. This lowercase p of x is the probability per change in x. Now, if you add up the total area under the curve, you get 1. And if you've had calculus, you might understand what this symbol means. This just says, find the area under this curve from -infinity to infinity, and you'll get 1. If you have never taken that class, don't worry about it. The symbols aren't important. The most important takeaway here is that the area under the curve is 1 because the total area corresponds to probability. Now, if we're talking about the probability that x is between A and B, if we want to find that probability, we can look at the area under the curve between these vertical lines, x equals A and x equals B. And that's represented by this symbol from calculus. But again, I just want you to understand the correspondence between area and probability. So in this example, it looks like h is the variable instead of x. And they're saying the probability that h is between 0.6 and 0.8 is this area here. And it turns out that that area happens to be 0.400. So you take the area under the curve for a range of values of that continuous random variable. So that range of values for the continuous random variable is down here on the horizontal axis. And the area under the curve and between those two vertical lines tells you the probability. Okay, so let's summarize. Chapter 5 was about discrete probability distributions that describe discrete random variables x. In chapter 6, we're going to study continuous probability distributions, which describe continuous random variables x. In chapter 5, each outcome x is associated with its probability. The sum of the probabilities must be 1 because something has to happen. And if we want to visualize that, we can visualize that with a probability histogram. If we add the heights of these rectangles, we get 1. Or if we require all of the widths of those rectangles to be 1, we can add the areas of the rectangles. Now, with a continuous random variable, rather than associating each x with a probability, we're describing the entire distribution with a probability density function, or PDF, given by p of x. Now, this is going to associate probabilities for a range of x values to areas under the curve, like we did here. So if h is between 0.6 and 0.8, the probability is this area. Now here's an example. The heights of men are normally distributed, and we're going to talk more about what that means in the next few videos. And they have a mean of 68.6 inches. If I am interested in this area here, what that represents is the probability that the height of a man is greater than 72 inches. If that area is 0.1123, as it says here, what that's telling us is that the probability that a man is more than 72 inches tall is equal to 0.1123. So there's an 11.23% chance that a man is more than 72 inches tall. So that's what that says. Now, let me go back here again one more time. This image came from a video called Why Probabilities of Zero Do Not Mean an Event is Impossible, or something like that. I may be butchering the title, but if you hover over this image and the other images that look like this in these slides, it will take you directly to that video. So what I'd like you to do if you're taking my class is I'd like you to watch that video next, and it helps explain this idea. Grant Sanderson from 3 Blue, 1 Brown does an excellent job of explaining the idea. I think he does it better than I do. But I'd like you to watch that video to get a better sense of these probability density functions. Now, I think the title of his talk or his video is Why a Probability of Zero Does Not Mean an Event is Impossible. Back in chapter 5, if you had a probability of 0 in your probability distribution table for that discrete probability distribution, we would say if it's discrete, yes, a probability of 0 means that that event is impossible. But over here, probabilities aren't associated with X values. Probabilities are associated with a range of X values or a range of values of that discontinuous random variable X. And then when we're actually finding the probability, what we're really doing is we're finding the area under this probability density function, or the area between that function and what would traditionally be the x-axis. So if somebody asked me, oh, well, what's the probability that h is 0.5? And we're talking about a continuous random variable h. Well, the area under the curve in that case would be 0 because there is no width. It would just be a line segment, just straight up and down. In order to get an actual probability, we'd need some area. So rather than asking, what's the probability that h is 0.5, we might say, what's the probability that h is between 0.49 and 0.51? What's the probability that h is in this tiny, tiny range? We could find that, or we can find that. We can often find that using the methods in the rest of this chapter. So please check out Grant's video. That's the next one on our playlist. We're going to keep referring back to ideas from his video in the lessons and the videos for 6.2, 6.3, and 6.4. So I highly recommend that you check that out now because we're going to keep revisiting those ideas.